So hello everyone. On behalf of all the convenors and SCAR, we welcome all of you to this session. The title of this session is Physical Drivers and Climate Implications of Antarctic Sea Ice Variability and Change. I am Dr. Babula Jena. Will be coordinating this session along with Dr. Anil Kumar and Dr. P. Sabu from NCPU Goa. Unfortunately, one of the convener, Professor John Turner from British Antarctic Survey, is not available, and he has apologized for not being able to participate in this event. And we had proposed this session in view of the importance of Antarctic sea ice variability in modulating weather and climate system, Southern Ocean circulation, cryosphere ecosystem, biogeochemical cycle, and many other aspects. And in this session, we have received total of 31 abstracts with 25 of oral presentations and 6 e-posters. Today we have 8 oral presentations, and rest of the presentations will be on tomorrow at this point of time again. So before I introduce our keynote speaker of this session, I would like to mention 4 points here for the speakers. Number 1, each speaker has 12 minutes for oral presentations, except keynote talk of 30 minutes. So please try to spend 10 minutes for your presentation, followed by 2 minutes for the question and answers, questions and discussions at the end of your talk. And second point is any queries and questions, it can be asked using the Zoom question and answer function. So we'll keep a watch to find out the appropriate question, and we'll push the questions to the speakers. And third point is the organizer is planning to record and upload the videos in the YouTube channel. So if at all you are not interested to upload your videos, or you don't want to record your videos, please intimate to the organizers before 12th August 2022. And in this session, there are 6 e-posters which are available in SCAR website. So all the participants can view and comment on the posters online. And next, this session's keynote speaker is Dr. Tom Bresgiddle. He'll be talking about Antarctic sea ice projections for 21st century. Dr. Bresgiddle leads the Polar Climate and Prediction Group at the British Antarctic Survey, UK. Most of his current research focusing on improving process understanding of polar climate variability and change, and its linkage between polar and extrapolar regions. So over the last decade, he has held a number of positions in SCAR groups and is currently co-chief officer of the Antarctic Climate Now Scientific Research Program. Today, he will be talking about how the historical sea ice cover helps to constrain Antarctic sea ice projections. So now let me welcome Dr. Bresgiddle to start his talk. Tom, the floor is yours now.
Thank you very much, Babula, for that, or Babula, for that excellent introduction. And thanks very much for inviting me to give this keynote presentation. It's really work that Caroline Holmes has been doing. She's the lead author on the paper that this is derived from. She's currently on maternity leave, so can't be here to give the talk. And I'd also like to thank Paul Holland, the other co-author on the paper, and then Tony Phillips, Scott Hosking, Letty Roach, David Stevenson, and the CMIT modelling groups, who make such a huge contribution to our science. So yeah, so we're looking at using observed historical ice cover to help constrain Antarctic projections. And so this talk will really be quite a big picture talk about whole Antarctic-wide changes and implications, and will hopefully lead into some of the more detailed discussions that will come later. I know this is a diverse audience, so I'll try to speak slowly, But if anything is unclear or you don't catch anything properly, please do ask questions in Q&A, and I'll do my best to answer them afterwards. So I'll start off. So all this talk is about projections and it's about sea ice. I'll start off a little bit looking at historical sea ice and also a motivation as to why, the implications of sea ice change for the wider climate system over Antarctica, and then go into detail about the work that Caroline has been doing on this project. So I'll also bring up a little pointer so that I can, there we go. So just a few days ago, I brought up the latest Southern Hemisphere extent anomalies from the National Snow and Ice Data Centre. And July 2022 for Southern Hemisphere sea ice extent looks really quite anomalous in the modern satellite era. So through this year, we've had a series of monthly low sea ice records, and July has joined in with that. And so this partly illustrates this complex picture of variability and change for Antarctic sea ice, which has been behind some of the questions about how we can trust climate model projections. Are we getting the processes correct? Which aspects can we trust and which aspects are more difficult to represent? So that's part of the story. And then if we think about climate projections of sea ice area and sea ice extent, it really is an important parameter to get right. These plots here from England et al. In 2018 show Antarctic surface temperature change as a response in a climate model simulation sensitivity study to sea ice decline across different seasons. And you can see surface temperature anomalies of a few degrees centigrade, particularly in winter, not just over the regions of sea ice, but also over quite large parts of coastal Antarctica and into West Antarctica as well. If we look at another variable, zonal wind change, there's also a sensitivity in the same simulations that they conducted. As the Antarctic sea ice retreats, the equator to pole temperature gradient decreases, and so we have a weakening of the westerlies in these simulations. And so this weakening of the westerlies happens all year round, but it's slightly stronger in some seasons. This is highly relevant because we have a large range in projected estimates of how sea ice area might change, sea ice extent might change under future climate scenarios. There's also a very large uncertainty in terms of projected jet stream changes as well. And so some of the work that has been sort of a lead into Caroline's work looked into these different factors. And part of that work, we generated diagrams like this, where we have a scatter plot, and on one axis, a sea ice related parameter. In this case, this is sea ice response over the 21st century, following, in this case, the RCP 8.5 high emissions scenario, CMIP5. And then along this axis, jet speed response. So that's the speed of the westerlies that flow around Antarctica. And consistent with England et al. 2018, models that have a large decline in sea ice area have a weaker change in jet speed response. So there's other things apart from sea ice that cause jet responses, but you see a weaker response. The thing that I guess is partly motivation for the current work is also that not only just the sea ice response related across the models to jet speed responses, but also the historical climatology. That's important because the historical climatology is an observable quantity. So this is something we can measure. And if we can correlate across the different CMIP models, so these are all different CMIP 5 models with some future projection, in this case, jet speed response, then it does raise the question as to whether we can use this information to guide which of these jet speed responses might be more or less reliable. So these models here have far too little sea ice in their historical climatology. And they exhibit much stronger responses in the jet speed response. So these models, they have very little sea ice. There's very little that they can melt, so there's very little sea ice change into the future. This type of diagram is referred to as an emergent relationship across a multi-model ensemble, whereby some historical observed quantity can be related to some aspect of future projected change. If we are confident that we understand where this relationship comes from, what the physical basis for it is, then there's a basis for using this information to actually constrain the projections, and we call that an emergent constraint. So in this work, which was mainly looking at jet stream changes, we saw this linkage to historical sea ice climatology, and led to the question as to whether what we can say about projected sea ice change and the extent to which we can understand that linkage. So this plot here is a similar scatter plot to those I've just shown, but it's just showing historical sea ice area on this axis and projected sea ice change following the RCP 8.5 scenario on this axis. This particular plot is annual mean. Come on to that later. And the dashed line here shows the satellite-based estimates of, or one satellite-based estimate of historical climatology. So if you look at a time series of sea ice, in this case sea ice area, I'm sure I don't have to explain to this audience the difference between sea ice area and sea ice extent. If we look at the historical record, we've got this includes 2 data sets, and you can see that our estimates of reality, the range of the observations is far smaller than the range across CMIP models. The different colors here represent different scenarios. The main point of this plot is really just to show the range across the different models, and the fact that there's quite large year-to-year variability as well. There is, of course, also the question of the observed changes, where most of the models have a general decline in sea ice area, and observations have shown a slight increase and then a more rapid decline more recently. That's actually something that we won't discuss much in today's talk, but it could be something for discussion afterwards. So key questions that were addressed in this work. First one is a comparison between CMIP5 and CMIP6. So this work here was really looking at CMIP5. And then to consider different seasons. So this plot here is for annual data. So we were motivated to look at different seasons as well. Main data sets that were used, the NASA team and Bootstrap for the observational or remote sensing data sets. And then CMIP6 data. We used SSP 585, high emission scenario, but also other ones as well. I'll show results for them. The sea ice area, it's calculated from sea ice concentration, or pre-provided sea ice area diagnostics. There were 34 CMIP5 models available for this study as well. So if we look at, start off looking at summer. So as you know, there's very little sea ice in summer around Antarctica. And look across both CMIP5 and CMIP6. So first, if we look at this plot here, I'll take a little bit of time to explain what's on here. So on this axis, we have historical sea ice area. And then this axis projected change. And this is change over the 21st century, so end of 21st minus end of 20th. The blue lines are CMIP6 models, and the red lines are CMIP5, and then the two remote sensing data sets shown here. So in summer, you can see that in the CMIP6 models, there's a very strong constraint related to the fact that most models lose almost all of their ice by the end of the century. So models that don't have sea ice, they have very little to lose. The CMIP5 data set actually has a few more models that have large sea ice areas in the historical climatology. So this represents possibility of a slight improvement in CMIP6, where these high bias models are no longer present. In order to compare the two data sets in a different way, well, they compared it in two ways, one of which just taking the whole ensemble, and another way looking at the same range across historical climatology. If we use the observational data to estimate future change from the models that most reliably reproduce historical climatology, we get estimates of future change from that approach. Then we end up with diagrams like this. And the implications of using these relationships to make projections. So the first thing to say is that these best fit lines, the shading shows the uncertainty of the best fit, the mean response, the best fit, and then the dotted lines show the prediction interval around that. And it's quite clear that if we use that relationship, that best fit line, our estimates of future change based on that are shown here by these box and whisker diagrams. Whereas if we just take the whole ensemble unconstrained, we get this range in CMIP6. And you see a slightly similar picture in CMIP5. So the implications of this constraint are a narrower range, a narrower uncertainty. The models with more realistic present-day sea ice suggest near zero loss is not really possible, at least in this context. The mean prediction is for greater loss than the raw ensemble by itself. So that's the mean prediction if you just take all the models, and that's if you apply this constraint. If you take the subset of CMIP5 models with a similar range of historical climatologies and without the high bias models, the results look more similar to CMIP6, but there is still an offset. And there does seem to be a sense that the CMIP6 models are more sensitive to external forcing. And that's something we'll come back to. Okay, so this physical limit argument, where models can only lose ice that they have, in a sense, it only really applies to the models that lose all their ice by 2100. So one way to look at this in more detail is to isolate those particular models. Let's say group 1, all ice lost. And these are identified by this approach. So you identify the year at which all the sea ice is lost in those models. And you can see here, many of the CMIP6 models lose their ice before 2100, so you've got time on this axis. And then on this axis again, we've got sea ice area, historical sea ice area. So in group 1, the correlation between sea ice area and future loss is very high, unsurprisingly. And this group dominates CMIP6, so 20 to 26 models in CMIP6. The models in group 1 with less historical sea ice also lose ice sooner as well. So there's a sense in which there might be some predictive power for the timing of loss as well as the extent at 2100. The group 2 models, so those are models for which some ice remains. And for the CMIP5 models, 12 out of 34 of those, most of the CMIP5 models are in that category. And for those models, there is still an emergent relationship, but it is weaker and dominated by other processes. So that's the picture in summer. In September, in the maximum, I guess it's not quite summer, end of summer, or end of winter, sorry. The models, again, with the models with more ice still lose more ice, and this statistically significant relationship, but it's weaker than summer. So we see these relationships here for the CMIP6 and the CMIP5 models. The multi-model, the unweighted multimodal mean, which is the cross lines here, show quite similar results to the, or quite similar climatology to the remotely sensed data. So that in that sense they do pretty well, but there is a very large scatter. If we look at the implications of using the best fit line to make projections, again we can look at plots like these, and a similar picture to summer qualitatively is that we have slightly greater loss in the constrained models than in the unconstrained ensemble. And also, there is an offset. So the CMIP6 models show a greater decline in CMIP5. So they both have a similar slope, but there is a significant offset between the two. And of course, many of you will know that the CMIP6 models have a higher climate sensitivity on average than CMIP5. And this was an obvious starting point to try and identify where this offset could have come from. And this plot here shows pretty clearly that there's strong evidence that higher climate sensitivity is related to the more rapid sea ice loss in CMIP6 compared to CMIP5. So along this axis, we've got global surface area temperature change. I should have labeled that. Versus Southern Hemisphere Antarctic sea ice area change, again over the 21st century. And the sea ice loss on the y-axis is correlated with global mean temperature change, and the relationship is indistinguishable between CMIP5 and CMIP6. They pretty much lie along the same line, which is quite remarkable in a way, in the sense that these are different multimodal ensembles with different ranges of historical climatology, but it's very clear here as well that the CMIP6 models here with a higher global, well, this is a sort of transient change, but they do have a higher climate sensitivity as well. Those, according to this diagnostic, very clearly seem to be exhibiting greater sea ice loss. So I think we can say with quite high confidence that the greater sea ice area loss in CMIP6 is related to greater warming. So, key points. We compare CMIP5 and CMIP6 projections of Antarctic sea ice loss, assessing drivers of uncertainty and the robustness in projections, at least one aspect of them. Under storm forcing, the CMIP6 models lose some of sea ice by 2100, so this does exert a constraint based on historical climatology. And the increased winter sea ice loss, and possibly summer as well, are related to increased climate sensitivity in the CMIP6 models. However, and I think probably I've covered most of these points. So we have summer and winter contrasts. But if we think about outstanding questions, there's a lot left behind here in many senses. I think that, the main point to consider is that, regardless of simulation processes or trends, an accurate representation of climatological mean sea ice cover is a necessary condition for accurate projections. However, what's missing? There are certainly a number of known unknowns. It's possible that all or most climate models have CS area that changes too rapidly due to ensemble-wide biases or missing processes. There's evidence of slower decline in high-resolution simulations from Rakov et al. We've just seen the impact of the higher global climate sensitivity projections, and then there's the lack of freshwater input from ice sheets. That's a major topic of research at the moment as well. And then, of course, this statistical framework to rigorously exploit emergent relationships in sea ice projections. A more comprehensive statistical framework would be required as well. And then, we've obviously looked at baseline climatologies, but this issue of trends in observations and models. One of the reasons we didn't look at that in too much more detail is that there's large uncertainty across the different models and observations in terms of what's driving the trends. Makes the evaluation very, very difficult in terms of if the observational uncertainty is large in these emergent relationships, then it's very difficult to say something about the future projections. So I hope I've given you a good overview of the sort of larger scale picture of how projections are panning out in the CMIP6 models and related to CMIP5. So thanks very much for listening. I'm very happy to answer questions. I'm looking forward to hearing more details from the talks coming up. Thank you very much.
Tom, let me congratulate for your excellent talk on the CAS projections for 21st century. And you have a question here. So what would be the reason for increased warming in CMIP6 models? Could you hear me? Can you unmute? Yeah. Yes. Yeah.
Yeah. So that's the larger global climate sensitivity, and that's largely thought to be associated with differences in representation of clouds. So that's something that, yeah, we didn't really look at too much in more detail in our study.
So I would request the audience, if you have any questions, please. You have still 5 more minutes, so 4 more minutes. Okay, Tom, can I ask a question?
Yeah.
Tom, can I ask a question?
Yes, please do. Yeah.
Am I audible, Tom?
Yeah. For some reason, the microphone wasn't picking me up, but I think you can hear me now. Can you?
Am I audible?
I can hear you.
Yes, you're audible. You can go ahead.
Yeah.
No, that.
I can hear you.
Yes, yeah. Tom, if you look at the observations or even global reanalysis, the Southern Ocean sea surface temperature and even the salinity is basically cooling and freshening. The opposition is cooling and freshening. So that is mainly because of you have polar stratospheric cooling induced some changes, Southern Annular Mode changes. So I was just wondering whether all these features are being assimilated in the climate models to have a realistic projections.
That's a very, very good question. Yes, so these free-running climate models have have representation of stratospheric ozone depletion, the ozone hole, and an increase in the SAM associated with that in the westerlies. And so that has been found to impact on sea ice area in the models. Their modeling studies have identified a behavior referred to as a 2 timescale response to westerly wind changes, whereby the fast response is like the cooling and expansion of sea ice around Antarctica. And then a longer term response kicks in where you have, I'm dipping into oceanography here, so this isn't my area, but the slower upwelling of warmer circumpolar deep water up to the surface that through a process that acts on longer timescales. And so the idea is that may be taking a little while to emerge. And if this is happening in reality, if this timescale is a bit longer, then it could be part of the picture as to why we're seeing more rapid declines of sea ice delayed after the change in the westerlies. There's a nice review paper on that.
Okay.
Holly Ayres, I think. Ayres, anyways, is her name.
Thanks, Tom. You have another question. Does the Antarctic sea ice behave similarly in the pre-industrial control simulations in CMIP 5 and CMIP 6? Can you have a look into your question and answer this function of Zoom?
I see the question now. Does it behave similarly? I'm not clear on what sense. So Ryan, if you could ask, maybe type again, which, in what sense are you asking, does it behave similarly? Variability, okay.
Variability.
Does the variability change? We didn't look at that. It's a good question. And actually, it leads on to another point I was going to make is that, this evaluation of the models based on the mean state climatology, it's quite limited. There's a lot missing from that. And we're certainly going on to look in more detail now at how models handle rapid change events, for example. In terms of predicting how the future may evolve, we need to know how well models actually handle these extreme events or rapid changes in variability. So that's a key thing to start looking at in more detail.
Thanks, Tom, for answering all these questions. I think there is one more question. Hi, Tom. Do you have some ideas on how much the sea ice area bias from present days can change the future trend? Are there any models with better simulations on present day showing different response in the future?
So there are how much the sea ice area bias from present days can change future trend? Certainly on the emergent relationship plots I showed comparing historical climatology and future projections illustrates a strong relationship across the models. I don't know if I can very quickly share my screen, but it's probably easier just to
Thanks, Tom, for answering all these questions. Actually, because of time limit,
yeah,
we'll move to the next speaker. I'm really sorry for it. I think hopefully you'll understand.
I'll type in a response to that one.
Okay, thank you so much, Tom.
Thank you.
Thanks a lot. So may I please invite the next speaker, Professor Edward Blanchard Wigglesworth, and the title of his presentation is impact of winds and Southern Ocean SSTs on Antarctic sea ice trends and variability. If Professor Edward is available right now, I request him to start his presentation. Yeah, he is available. Yeah. Yes.
Yeah. Let me share my screen. So I hope you can all see that.
Yes.
Can you see that? Is that a yes?
Yes. Yes. Yes.
Okay.
Yes.
Thanks for the opportunity to share this work, and Tom's talk's a pretty good segue into my talk, and I'm going to discuss the impact of winds and Southern Ocean sea surface temperatures on the observed Antarctic sea ice evolution, specifically trends and variability. This is work mostly done at the University of Washington by myself and colleagues Letty Roach, Aaron Donahoe, and Qinghua Ding, who's currently at UC Santa Barbara. So on the left, I show you the well-known time series of Antarctic sea ice extent in the observational record in the satellite era from 79 to present. And we kind of long-standing problem in Antarctic climate science is that climate models generally struggle to simulate the observed trends. Right, so in observations, we've had a weak positive trend of sea ice during the last 4+ decades. And on the left, I show you a plot from Rosenblum and Eisenman 2017, and they looked at CIMIP-5 models, and they showed that generally they simulate negative sea ice trends, which is maybe what you'd expect from global warming. And this issue is still present in CIMIP-6 models, which is shown on the right. The figure on the right shows a histogram of trends in sea ice extent, and you can see that the green values are those from CIMIP-6 models, and the observations, and we show here 3 different estimates of the observations. They're sort of very much on the edge of what climate models can simulate, which again in CIMIP-6 generally show negative trends, again, which might be what you intuitively expect from global warming for sea ice to melt and trends to decrease. So this is still a little bit of a mystery of why the observations have done this, and there's been a lot of work, and our own contribution has been sort of geared to kind of answer the question at the bottom. They can see that if you know what the observed winds and the Southern Ocean sea surface temperatures to the north of the sea ice, if you know those, what would the sea ice be doing in these models, and can they help you understand the sea ice trends but also the year-to-year variability? So to answer this question, we've used a CIMIP-5 climate model nudged to the observed winds and Southern Ocean sea surface temperatures. So climate models, or CIMIP-5 and CIMIP-6 climate models, are generally, well, not generally, always free running. So the results, say from Tom's talk, are from free running model simulations. And in this experiment, we took one of these models and basically fed into it the observed winds and sea surface temperatures from 79 onwards. And in these domains, you can see on the bottom left, you can see the global domain of where we apply the nudging, and the kind of red shading, that is where we applied the wind nudging. And the green box is where we applied the SST nudging. And we were quite careful when we nudge SSTs to only nudge SSTs north of wherever there's sea ice. Because if you nudge SSTs where there's sea ice, then you kind of feed in the answer into the sea ice. So that's kind of a key point. The tropics, or anything between 45 south and 45 north, is left free running. So the model, there's no nudging over that domain, which in terms of areas is almost 2/3 of the planet. We run 2 different sets of simulations, one where we just nudge the winds in those domains, and I'm going to show those results in red. And then we have 2 more runs, or 2 more simulations, where we nudge both the winds, and these are winds in the atmosphere, and we also nudge the SSTs. So we nudge both together in these additional runs. And for each of these sort of nudging setups, we have two different simulations, and the only difference is the initial conditions. And one of them samples low initial conditions in 1980, and the other one samples climatological sea ice conditions in 1980. And the reason we did this is to see if that had an impact on the long-term trends, right? Because when we start taking observations in 1979, because we don't really know what happened before, we don't really have much of a sense of, was that a close to climatology, or was it perhaps really negative years, and we're kind of starting to sample from a kind of anomalous years. Okay, so on to the results. In blue, I show you again the observed time series. In black and gray, this is the CSM lens large ensemble, so the CSM1 count 5 large ensemble. The black is the ensemble mean. The grays are the individual members. There's 35 runs in this ensemble. And you can see that, yep, the model has a negative sea ice trend, as you expect from the CMIP results. And no single member, you can see that really gets close to observations. When we nudge the winds, we obtain the two simulations here shown in red, bold and dash. Again, the difference between the bold and the dash are just the initial conditions. And there's a couple of things to note here. One is that this simulation, it doesn't sort of superimpose on the blue simulations, so it's not a perfect reproduction of the observations, but you can see that some of the variability year to year is captured, especially from the 1990s onwards. And also you can see the trend in the red runs is less negative or flatter than that in the gray runs, right, in the free run in large ensemble. The other thing to note is that the difference between the two runs that you can see in the initial conditions in 1979, within a few years, those differences kind of go away. And you can see that the initial conditions don't have much impact beyond about 5 years. For the other runs where we nudge the winds and the sea surface temperatures, two main things to note is that the year-to-year variability is very similar to the previous runs that only nudge the winds. So you can start seeing an answer that in terms of understanding interannual variability, the winds are kind of the main factor. But in terms of the trends, you can sort of see that for the first half, the magenta runs are below the red runs, and then for the second half, they have high values. So the trends are a little more positive or less negative. And to show you that a little more clearly, the correlation, by the way, the detrended correlation is around 0.5 or 0.66 for the kind of the 2/3 from 92 onwards, which is when these runs actually match the observations fairly well. One point to make is that regionally, these simulations do quite a bit better, which I'll show you in a minute. In terms of the trends, this figure shows the trends in sea ice extent every month for the observations and then the model simulations. And again, I show in lens the black and gray, and in red are the wind nudge runs. This is from 79 to 2018. So a couple kind of points to make is that when you just nudge the winds, the trends are less negative. They fix about 40% of the model bias. So they get closer to observations, but they're still quite a bit more negative than the observations. And they lie at the upper limit of what the free running model can simulate. When you nudge the winds and the sea surface temperatures north of the sea ice, you're getting pretty close to observations. These runs actually are not significantly, the trends are not significantly different to zero, which is indicated by the kind of the dots. So if you see a dot on the values, that means the statistical significance. And you can see that the magentas are just under the zero line and quite a bit closer to observations. When you look at 1992 to present or 2018, we can, by nudging the winds and the SSTs actually explains the trends really well. And we even monthly, during the months for about 2/3 of the year outside, late summer, early fall. We're capturing the observed trends really well by nudging the winds and the SSTs. When we look at taking a regional perspective, these panels show the sea ice extent in 6 different regions across Antarctica, which are shown in the top left. And you can actually see very good agreement between the nudge runs and the observations, especially in West Antarctica. So if you look at the Ross, the Amundsen, and the Bellinghausen, there's really good agreement, both in terms of interannual variability and the trends. There's a little less skill in East Antarctica. So if you look at the Southwest Pacific and the South Indian, there's a bit more of an offset. There's a pretty interesting feature in the South Indian where there's very good agreement up to about 2001, and then for about 15 years, the observations, there's quite a bit of sea ice gain there, which the nudge runs cannot reproduce, and then from 2015 onwards, they agree again. So this is quite interesting that regionally we actually see better reproduction than in terms of Pan-Arctic sea ice extent. Going back to the results that nudging the winds, it does improve the trends, but only about 30 to 40%, and you really need to both nudge the winds and the SSTs to get close to the observations. Basically, we found that the model warms too fast, right, from 1979 to 2018, and these panels show temperature trends globally on the left panel, Southern Hemisphere in the middle panel, and over the Southern Ocean in the right panel. So x-axis are temperature trends, and the y-axis are Antarctic sea ice extent trends. And you can see this really strong coupling actually across all simulations, both in CSM lens and when we do the nudging. And you can see that in observations, they actually fall, especially for the Southern Hemisphere, they fall right in the relationship that the model reproduces, right? So, you could almost just say, well, if the model had the right temperature trend, it would have gotten the right Antarctic sea ice extent trend, which I think is less trivial than it sounds.
You can in 2 minutes.
Yeah, so this is my last slide. We find that that's the key aspect, or one of the key aspects in these results, that the model warms too fast, and by nudging the SSTs, you kind of accounting for that. This agrees with some independent work, and we wrote a short piece on NEOS, but I'll just leave the summary slide there. And thanks for listening.
Yeah. Thanks, Edward, for your nice talk on Antarctic sea ice trend and variability influenced by winds and SSTs. I could not see any questions in the chat box. Thank you so much again. And let me invite the next speaker, Professor Stephen Clay, who will be talking about winds, waves, and ice production rates in the terrain of Bay Polynesia.
Thank you. Just want to get can you see my screen okay? Can you see my screen?
Yes.
Yes.
You could see.
Sorry, I want to go back a little bit here. Thank you. We're going to switch from the model world to a different world, observations. And the title of my talk is Winds, Waves, and Ice Production at Terranova Bay, Polynesia. And this is a result of the Piper's expedition was made in 2017 between April and June. And just concentrate on the area in the south where we see the coastal polynyas and the Ross Sea developing in the Terra Nova Bay on your left part of the box and in front of the Ross Ice Shelf. And the polynyas develop because of the onset of the katabatic winds. And from satellite imagery, we can see the development of the polynyas with an open water reach. This is the Terra Nova Bay polynya in the image on the left. And the lower image shows the repeated tracks we made in early May for about 12 days in and out of the Terra Nova Bay, making a variety of ice, ocean, and atmospheric measurements. So this is a radar satellite imagery, because of course the visible imagery is not available there, and you can see that there's a characteristic development of the polynya as well. These shots show the in the early stages taken from a camera, two cameras mounted in tandem. There's on board the ship, there's a open water reach and an ice band in that area, and the right-hand image shows the surface temperature, which is pretty uniform throughout this area. And later on, what we're seeing is in the interior of one of these ice bands, we're seeing the development of pancake ice, which you probably see better in the infrared image, the small pans of ice that were developed. And this is a very characteristic of wave formation, is development of pancake ice. And also the surface temperature is colder in these pans than it is in the surrounding loose fragile ice around it, a key point later on. As you get outside the polynya, we see these highly rafted pancake ice. The dimension on these pans is about 0.5 to 1 meter across. This is taken off the side of the ship, and there's a gauge that's sticking out from the side of the ship that we can measure the diameter of these. And this is the highly rafted area that we're seeing, where you can see the many of the pancakes upturned on edge. So we're seeing characteristic wave formation of ice in this area, far removed from the outer ice edge where we typically see waves. To measure waves, we used what are called swift buoys. I won't go into detail on these, but one of the measurements they make is high frequency measurements of waves. And on the right-hand side, you can see in the second panel, the significant wave heights exceeded about 2 meters in these swift buoys for this one event, a long-term event that we had for about a 13-hour deployment of the swift buoy. And characteristically, these are the swift buoy observations for that period, ranging from the early part of the deployment up through about 12 hours later on. In the early part of the deployment, the swift buoy was deployed in one of those open water bands that I showed, and the characteristic spectra shows a large high frequency content. And then as the buoy became incorporated within one of those ice bands, we're seeing the attenuation of the high frequency waves as we go further down. And this bears on some of the measurements I'll be talking about in a moment. From this, we were able to measure the wave heights for this particular event. And you can see that as the buoy was advected further out, we see a decline in the wave action because of the attenuation of the ice. But as I showed in the previous slide, there's a high frequency component that's declining as it moves from the open water bands to that. A key measurement that we wanted to make was of breaking waves, which is the integral over the high frequency spectra. And it results in the mean surface slope shown in the bottom graph here. And in the open water band, we're seeing much higher mean surface slopes indicated of breaking waves in the open water band, which you can see visually in the top image as well. And then a rapid drop off as the buoy was incorporated into that of the mean surface slope because of the decline in the wave spectra. And the low frequency component from the previous slide is not very highly attenuated until we get much further out. So that's the wave action. We're seeing not only waves in there, but breaking waves. Another measurement that we made was the heat fluxes. And this was done by a series of transects across the polynya, where radiosonde balloons were laid out at the intervals P1, P2, P3, and P4 on this particular transect. And the baseline station was the automatic weather station called Manuela, located just on the edge of the Nansen ice shelf on the coast. And the integral method allows you to measure if it's a fairly stationary condition, which it was with the decline in the wind speed, no decline in the wind speed observed over this area. You can take a look at the method of integrating the heat fluxes between the two different radiosondes or measurements here. So P0 to P1 would give you one integral, P1 to P2 another, and so forth. So you can see the change in the heat fluxes that were measured over this period. And what was found was that there are relatively high heat fluxes of the order of 2,000 watts per square meter, especially in the interior region of this particular area. So this just shows the direction of the ship transect and the launch of the radiosonde balloons. And these were done in conditions very extreme, probably 25 meters per second wind speeds that were launched there. So not a trivial task to launch a radiosonde from a ship in that time. Now the heat and moisture fluxes, surface fluxes by the bulk method can be estimated pretty accurately. The sensible heat flux equation is shown here in latent heat flux. And normally it's straightforward to estimate fluxes because these are fairly easy to measure and they were measured on board the ship. A little variation in the coefficients of heat and mass transfer, and there's a well-known stability correction. But when you do this, you find that the heat fluxes by the bulk method are very low compared to only about half, especially in that interior region of the polynya. Were quite low, about half of the 2,000 watts per square meter that were measured by the integral method. So what's the problem? And the problem is sea spray. When we have breaking waves, we have a high concentration of sea spray that shows an observation where it's clearly seen. And from some work done in tropical cyclones by the late Ed Andres, one of my colleagues, they found that there's a measurable amount of heat flux associated with sea spray, which was applied to this particular problem. And this shows the calculation of heat flux with interfacial, shown in red, the sea spray contribution, and the total sensible heat fluxes, which then got up to this amount of 2,000 watts per square meter, which was measured by the integral method. So there's nearly about half of the heat flux, especially in those interior regions where there's open water, can be associated with the presence of breaking waves and the generation of sea spray. And you see, as we go further out in the polynya, this is a distance from the ice shelf that we're going out and get into more and more ice-covered area. This drops off rather radically. And we do hit another area of open water where, again, we see relatively higher values of the heat flux, and there's a significant sea spray contribution. And the line in blue shows a decline in the sea spray contribution as the area becomes much more ice covered. The total heat fluxes are shown here, sensible and latent. The latent heat flux is much smaller, so it's primarily generated by the sensible heat flux shown in red, and the total heat flux has exceeded 2,500 watts per meter squared in the area closer to the ice shelf. We can calculate what the ice growth rate is in centimeters per day in this particular area, and we're seeing very, very high ice growth rates of the order of 60 centimeters per day in that particular area. Now, we don't get 60 centimeters of thickness because the ice is being constantly advected outward as it's growing. But if you take a look at a square meter of surface area in this particular area, you find that the growth rate over that square meter is going to be of the order of 60 centimeters, over 60 centimeters per day. So major findings in this is we have very high heat fluxes, a sea ice formation rate of 65 centimeters per day. Sea spray is important, contributing about half the heat flux in those near coastal areas. And there's some other results from snow formation, which I won't go into at this particular point. What we did was to estimate the heat fluxes and the ice production in May 2017, the entire month of May. We were there for.
Stephen, you have 2 more minutes.
Thank you. I'm just about finished. And the top panel shows the Manuela, using the Manuela automatic weather station. And these are the characteristic wind speeds in the top panel, air temperature and relative humidity. And the middle panel shows the components of the heat flux with the no sea spray contribution. The important result is the fourth panel down here, where we combine the total heat fluxes with the sea spray contributions that were calculated over the entire month, and we get the ice production in centimeters per day, which is shown in this graph on the left-hand side here, corresponding to those heat fluxes. So again, we're seeing these very high values in that period in May when we were actually measuring what those heat fluxes were. So conclusions, we have katabatic winds that generate waves. The breaking waves generate sea spray. You get high heat fluxes, doubling that seen from interfacial alone. High concentrations of grease or small pancakes suppress the sea spray and reduce the heat fluxes to interfacial values. The monthly ice production in May at mean values for the entire month of 30 centimeters per day, but 46 centimeters a day when the sea spray contributions included, and giving a total month of May, and this per square meter now is up to 14.4 meters per month of ice production within that. So very high. We have remaining questions and further studies, and I'll let you read those. We want to be able to eventually figure out the annual production, and figure out if similar conditions exist in other coastal lineages, and try to get a better handle on what the total ice production in coastal lineages is around Antarctica. Thank you.
Thanks, Stephen, for this wonderful talk. I just want to know, I just want to understand, how did you segregate out the interfacial turbulent flux and the sea spray flux? Because when you take interfacial turbulent flux, that also accounts for the moisture flux with all its transfer coefficients. So do it really require separate flux calculation? Is it bulk or is something different?
The bulk method is, the bulk method is based on the actual measurements on board the ship, and it's calculated fluxes from the bulk transfer coefficients, which are kind of well known in this particular case. They weren't actually measured as turbulent fluxes.
Okay.
But the bulk method works pretty well in most cases, and it agrees well with what we got from over the ice-covered areas. We get good agreement between turbulent fluxes and other measurements and what the bulk estimates are. So we're pretty confident the bulk estimates work pretty well, and they work pretty well over open water too. But the sea spray is a calculated value based on that the model developed by Ed Andrus and modified by Peter Guest to fit this particular situation. But I think it's an important consideration that even though there's a calculated value of the sea spray relative and the bulk fluxes, the bulk fluxes are based on measurements. The sea spray are calculated values, but it's important consideration that these are validated by the integral method that was a measured value from the radiosonde transects. So we have a known
Okay,
method.
thanks.
Yeah.
Thank you so much, sir. Thanks a lot. So, next, let me invite our next speaker, Mr. Mikhail Molchanov. The title of his talk is Effect of Polynya on the Structure and Dynamics of Waters on the Shelf and the Continental Slope in the Cooperation Sea, East Antarctica. If Mikhail is available here, please start your presentation. Or I think, okay, I would request SCART IT team, please play the pre-recorded video of Mikhail.
Hello. First of all, I want to thank the organization team for giving me this opportunity to present. Dear colleagues, my short presentation showing the research based on the data obtained in the Cruz Bay by Russian Antarctic expedition. Annual planning and methodological support for expeditionary research for the Southern Ocean as part of the seasonal work of the Russian Antarctic expedition is further assimilation and analysis of the obtained data. The ongoing observations are aimed at both ship-based oceanological observations and monitoring the interannual and climatic variability of the structure and characteristics of water masses in actual areas by repeating selected sections. One of these is section through 70 east longitude in Cruz Bay. These sections were done from 1998 to 2016, and cold dense water was found on all realization of the section at 70 east longitude in the area of the continental slope, which can be interpreted as Cruz Bay bottom water. The extended survey completed in 2016 made it possible to obtain a detailed picture of the mesoscale structure of water above the continental slope and the shelf area in the range of longitude from 70 to 71 east longitude. The polygon consists of 11 sections. In 2016, cold dense water in the area of the continental slope was found again. This dense water is produced by polynyas in the cold season, but expeditions were carried out in the summer. It means that Cruz Bay bottom water accumulates in huge volumes in the shelf depression, and the flow continues even in the summer. Using data from marine mammals (MEOP) project and satellite radiometers and atmospheric analysis, we can reproduce previous conditions in the winter, and we can verify three-dimensional numerical model results using 2016 survey. Data from the MEOP project shows seasonal transformation of the water on the shelf. Satellite data on the sea ice concentration shows that polynyas exist continuously for days and weeks. Red color on the map indicates that more than 25 days per month, this area is less than 30% of sea ice concentration. Area of Cape Darnley polynya increases up to the 6,000 square kilometers, while area of the Mackenzie Bay polynya up to 3,000 square kilometers on the edge of 30% of sea ice concentration. Atmospheric analysis shows a good matching on the temperature, pressure, and directions of the wind. However, reanalysis underestimated strong wind in the winter season. For instance, reanalysis shows 23 meters per second, and at the same time, automatic weather station measured 30 on average and 36 meters per second in the wind gust. It is important to estimate heat and salt flows from the open water polar surface, which are used for numerical modeling formation of dense water on the shelf. We are using a fluidity-com model adapted to a domain 1 kilometer by 10 kilometer by 6 kilometer total depth, shelf slope width, shelf length accordingly. With shelf width of 5 kilometers and shelf depth of 200 meters. On the scheme, Polynia is displayed in orange. It is defined by the salt flow in the center of the surface above the shelf area. Polynia width is 1 kilometer. Modeling of small-scale dynamics and transformation of water on the shelf and continental slope in Antarctica is executed in the mesoscale. For this purpose, the fluidity-com model is used in a full non-hydrostatic formulation. The results of three-dimensional numerical experiments based on the real topography of the shelf and slope bottom and on the basis of real atmospheric forcing are presented, showing the research capabilities of the model. An extreme south flow is set on the open water surface of a winter ice-free or near barrier Polynia due to intense dynamics interwater ice formation. The process develops into cascading of the dense water on the slope in 45 hours. The model reproduces the evolution of dense currents in the near bottom layer from initial meanders with horizontal dimension 200 meters. Model results show good agreement with the measured density gradients in the near bottom layer on the shelf slope edge area. Dense currents forms and scale match the survey measurements carried out in 2016 well. The model fluidity-com reproduces the development of convective circulation in the Polynia correctly. The near bottom dense currents on the shelf and slope are shown in the form of discrete meanders, which acquire and bright unstable vortex character. The pronounced discrete nature of shelf cascading when approaching the shelf edge was previously predicted based on the analysis of the field observation, as well as the formation of compensatory upwelling on the continental slope above the bottom layer of cascading development. There is a partial and sometimes complete agreement of the model geometric dynamic hydrophysical characteristics on the shelf and slope cascading with similar ones obtained on the basis of the analysis of field measurements obtained in the Bruce Bay as part of the seasonal work of the Russian Antarctic expedition. Such a coincidence in the result of a reasonable and correct setting of the initial flow conditions, and the model reproduces the dynamics and transformation of near bottom density currents well. That's all. I intended to say thank you for your attention. You are welcome to ask any questions on my presentation. Please use the email address on the slide to do so. Thank you.
Next, may I please invite our next speaker, Miss Quinn. She'll be delivering a talk on open ocean Polynia in the Cooperation Sea, Antarctica. Quinn, if you are available, please start your presentation.
Yes, can you hear me?
Yes, we can see you, and please make it full screen. Yeah, done. Yeah.
Okay. Hi everyone, this is Qing. Today I would like to talk about the open ocean planears in the Cooperation Sea, Antarctic. An open ocean planear is a planear that occurs offshore, where the CS concentration is lower than its surrounding area. Previous studies have found significant impacts of open ocean planears on ocean circulation, coastal and bottom water properties, and Antarctic ecosystem. This figure shows the average Antarctic CS concentration in September for 2002 to 2019. We can see certain regions, such as motorized planear, it has lower CS concentration than their surrounding areas, and here near Cape Ann in Cosmonaut Sea, and here in the Cooperation Sea. In this study, we show for the first time that in the Cooperation Sea, there exists a more persistent feature of open ocean planears. Here shows this table shows the data sets used in this study. This figure shows the time series of the total planear area in the Cooperation Sea for 2002 to 2019. The largest value of the total planear area reached 312.4 thousand square kilometers on 25th August 2010. Here shows the CS concentration pattern for this day. This value is close to the maximum size of the planear that reappeared around the motorized on 21st November 2017. And by using the size concentration threshold of 0.50, the largest values reached 170.5 thousand square kilometers on 3rd November 2018. To clearly see the seasonal variability, this figure shows the time series of the open ocean planear areas in the Cooperation Sea for 2018 and for motorized for 2017. The magenta lines are Cooperation Sea planear in 2018, and the green lines are motorized planears in 2017. We found that during the most winter times, the planear areas in the Cooperation Sea were considerably larger than that of the motorized planear in 2017. And the motorized planear reached its largest value on the following melting seasons in November. Next, I will illustrate the large-scale atmospheric and oceanic forcing machines.
I think your slides are not moving. Quinn, your slides are not moving, it seems. Your slides are not moving. Yeah. It is still in data sets used in this study.
I'm going to share my screen again. It's okay now?
Yes. Now it is visible. Yeah.
Okay. I will illustrate the large-scale atmospheric and oceanic forcing machines responsible for the Cooperation Sea planears. The shading color of this figure is the depth of the minus 0.5 degrees isotherm averaged over 2002 to 2019. We can see the subsurface warm water is is usually shallower in this region. The red line and the white line are the locations of southern boundary and Antarctic divergence. Since the ACC travels closer to the continental shelf in this region, the upper CDW migrates closer to the continental slope. So the AD is situated over the upper CDW. The cyclonic wind forcing associated with the AD causes sea ice divergence and promotes the upwelling of warm subsurface water. So the divergence of sea ice along with reduction in new ice, both contributed to the formation of open ocean planears here. On synoptic scales, this figure shows the effects of a storm on planear formation from 11th to 12th July 2012. There was a passing storm in this region on 11th July. The red star is the location of low pressure center. In the western portion of the storm, the winds are generally offshore, resulting in a zone of sea ice divergence. 1 day later, the storm moved eastward and caused the sea ice divergence in the west portion, which led to the eastward expansion of the planear. Here shows the sea ice concentration in the Cooperation Sea on 12th July 2012. Once the planear occurred, the ocean surface stress could increase substantially, owing to the removal of the sea ice in solution effects, which lead to the enhance of upwelling across the base of the mixed layer. The CLCDD data observe the entire duration of the planear from 10th July to 21st July. Here shows the location of CLCDD profiles. The different colors present the different days. This figure shows the vertical structure of potential density, salinity, and potential temperature for these CLCDD profiles on 10th, 12th, and 21st July. From 10th July to 21st July, with a deepening of the mixed layer from 66 meters to 100 meters, the average heat entrainment rate is estimated as 262.3 watts per square meter. By entraining salty water into the mixed layer could become further dense and hence be further deepened. We also found some planears formed in the region featured by canyons and drifts. In this region, the planears could expand solely under the influence of oceanic processes associated with the rugged terrain. Some planears were often observed along the 3,500 meters ice beds. The formation or expansion of these planears here are not necessarily associated with wind forcing. This figure shows the ice-free planears for every 6 days from July to October in 2012. For example, the wind stress score on 8th to 11th October are appeared to be positive. On 8th October, the low sea ice concentration were maintained. Subsequently, even with the positive wind stress score, the area of open ocean planear were expanded slightly. The Cooperation Sea is also characterized by eddies and cyclonic circulations. The observational and numerical results also indicate the presence of further offshore eddies in the Cooperation Sea. The monthly mean currents in this region shows the possible presence of the cyclonic circulations here. And the eddies and cyclonic circulations are also documented in previous studies. To summarize, in this study, we document the spatial and temporal patterns of the open ocean planiers in the Cooperation Sea, and offer the atmospheric and oceanic forcing machines responsible for the formation of open ocean planiers in the Cooperation Sea. As indicated by the southern ACC front and the southern boundary, the southern boundary is southmost limit of upper CW. The AD can AD can can situate it over the upper CW, which causes the phase divergence and promotes the upwelling of warm subsurface water. At smaller scales, intense storms can lead to strong phase divergence, and the Cooperation Sea is also characterized by eddies and cyclonic circulations. That's all. Thank you for your attention.
Thanks, Quing, for your wonderful talk. Can you please go to the last slide?
Okay.
No, last summary before this.
Is this slide?
Yeah, no, before this slide, summary slide, your summary.
Huh?
You have to go up.
Summary, up one slide. Before. No, I have a question. So can you please show your summary slide? Conclusion slide. Conclusion slide, yeah. It is not moving back.
But this is conclusion slide.
No, not conclusion. This is only thank you slide. Before this, there is another slide summary.
What? I don't know. Which
just go
next?
No, your slides are not moving.
Oh, okay.
It's still in thank you slide.
Oh, okay. I will sharing my screen again.
Yes. Yeah.
Okay.
Yes. So, why you have only the instability induced cyclonic eddies here? What about the anticyclonic eddies? Do you have only cyclonic eddies over there? Why you don't have anticyclonic eddies?
Do you mean the blue quivers? Yes, we have cyclonic circulations here, as we talked about, as we talked before. When the Antarctic slope currents travels over the canyons, the water goes downhill the canyon, and the water column stretches. So that make a negative vorticities. So there have cyclonic circulations here.
Okay, then these eddies are mainly because of you have Antarctic divergence, or it is because of the Antarctic slope current through that canyons it passes through and it forms it triggers for the formation of these eddies, and that helps for polynya formation. So do you mean to say the combined impact of all together, or?
I can't follow you very well, but the AD can situated over the upper CDW.
Okay.
And the sea ice extend advances northward across the AD. So the cyclonic wind forcing associated with AD can cause the sea ice divergence.
Okay. And what about that red one, the red dashed line? Red, one is the southern boundary of SEC. What about the dash red? One more is there?
That dot line.
Yeah, dot line.
Yeah. Can you?
What about the red dotted line? Red dotted line.
And
anyway,
I can.
No, Anil, that's fine. That's not a problem. So I'll just find out if any questions are there. Thank you so much, Queen. Okay,
thank you for
there are no
question.
questions in the chat box. So thank you once again for your nice presentation. And let me go to the next speaker. Okay, it's a pre-recorded video presentation. So okay, now let me invite our next speaker, Dr. Antonino Ian Ferrola, and I request the IT team to play the presentations of Dr. Ferrola.
Good morning to everyone. I am Antonino Ian Ferrola, a PhD student of the Polar Oceanography Group at the University of Naples, Partenope. And today I'm presenting the main results of our recent study submitted to Geophysical Research Letter, which deals with the Pacific-Antarctic ridge and its role in favoring the sea ice formation. As you know, monitoring Antarctic sea ice is essential for improving our knowledge of the Southern Ocean and its role in the climate system. In this study, we used sea ice concentration and sea ice extent daily data at 3.5 km resolution over the Southern Ocean and covering the 2002 and 2020 period. Data have been processed using MATLAB software to obtain maps of the sea ice concentration over the Southern Ocean for each month from May to December, averaged over the 2002 and 2020 study period. May represents the beginning of the winter period, thus the sea ice is at the initial stage of its growth. During the following months, sea ice increases significantly up to September and then decreases again with the beginning of the summer. As you can see, the key results provide observational evidence of the recurrent formation of two sea ice protrusions, one circled in yellow in the weather sea sector and the second one circled in red that extends up to 60 degrees south at about 150 degrees west. This is extremely evident during the winter months and is also in agreement with previous studies which observed a typical maximum sea ice extent in the Pacific sector of the Southern Ocean during the months between August and October with some annual variability. We especially focused our study on the Pacific sector of the Southern Ocean, and therefore we extracted the median sea ice extent to describe the sea ice edge position for each month. The monthly average sea ice median extent is represented by the different contour lines, which are superimposed to the bathymetry map of the study area. This figure points out the presence of the sea ice protuberance in the longitude band between 150 and 140 degrees west. Furthermore, the contour lines of the median sea ice extent corresponding to the western side of the identified ice protuberance are aligned to the Pacific-Antarctic ridge. At approximately 150 degrees west, the ridge reaches lower latitudes, moving from about 66 degrees south at 180 degrees to 60 degrees south at 150 degrees west, so that the maximum sea ice extent can be identified immediately further east of its position up to the latitude of the Udinsk fracture zone, which, as we will see, has a strong effect on the melting process of the sea ice. These characteristics are more evident during the winter sea ice growing phase, whilst the northern edge of the mentioned protuberance moves progressively farther east during the following months, under the Antarctic circumpolar currents and winds forcing. These peculiar recurring events might be associated with several oceanic and atmospheric processes. A primary role is played by decadal scale variation of atmospheric circulation in the southern hemisphere, linked to the Southern Annular Mode and the Niño Southern Oscillation. On the other hand, little is known about the sea ice variability shaped by the ocean circulation and the role played by regional bathymetric constraints. To this goal, we explored the effect on the Antarctic sea ice of the interaction between eddies and the Pacific Antarctic Ridge, a tectonic plate boundary located in the Pacific sector of the Southern Ocean. First of all, we observed that in this sector the ridge acts as a shield for the formation of the sea ice, diverting the southern ACC front and the polar front northward and allowing colder water masses to reach northerly location. The ACC deviation is confirmed by this map, in which we represented the mean position of the southern ocean fronts. They show that in the Pacific sector, the most meridional ACC fronts are shifted northwards and reach their maximum northern extension in the longitude band ranging between 150 and 140 degrees west. Furthermore, we cannot neglect that eddies play a fundamental role in the dynamical balance of the ACC, in the momentum exchange, and in the meridional heat transport. Previous study describing the mechanism of interaction between cyclonic anticyclonic eddies and the marginal ice zone showed that both cold and warm core eddies favor sea ice melting. Thus, to understand the connection between the eddies, the Pacific Antarctic Ridge, and the sea ice protuberance, we used long mesoscale eddy trajectory products provided by Sarto-Duax and distributed by Aviso for the 1993 and 2020 period. Eddy trajectories have been used to produce monthly anticyclonic and cyclonic eddy distribution maps over the Southern Ocean during the study period. The median sea ice extent contours for the month of August and December are also superimposed on the eddy distribution maps. Compared to the surrounding areas, the concentration of eddy downstream of the bar is lower than upstream the reef. The presence of the ridge represents a strong barrier that prevents cold and warm core eddies from propagating eastward and forces them to move northward, limiting their interaction with the marginal ice zone and determining that the sea ice extent contours generally follow the submarine relief itself for all the months analyzed. The effect of the Pacific Antarctic Ridge is also demonstrated by the absence of eddies downstream the ridge, even during the summer months, when the sea ice extent is limited to higher latitudes. This mechanism favors the sea ice extent exceptional growth at 150 degrees west, which is opposed only by sporadic anticyclonic mesoscale structures that reach the ice protuberance coming from east. Finally, the presence of few eddies south of the ice border may be instead associated with the Rothschild circulation, referring to specific months and years during which the sea ice extent and its concentration were limited. We integrate these results by analyzing for the 1993 and 2020 period cyclonic and anticyclonic eddies frequency maps, calculated in square cells of half degree per half degree, so to evaluate the areas where they are most concentrated. Each half degree per half degree square contains the number of eddies that passed through that cell just once, so filtering out the eddies recirculating in the same box. Thus, the color bar refers to the number of eddies that passed through a cell, and the black contour lines represents the isobat of 2,500 and 2,600 meters of depth, identifying the Pacific Antarctic Ridge position. As expected, the western slope of the PAR is characterized by a higher concentration of eddy than the eastern one. However, after the Udinse fracture zone, there is an increase in the eddies observation downstream of the PAR, since the ACC and the SDs are finally able to overcome the PAR itself due to the sea depth increase. In summary, as sketched in this cartoon, we observed that in the study area, the ACC represented by the orange arrow is evidently diverted northward by the Pacific Antarctic ridge. This implies that the related cyclonic and anticyclonic eddies arising from the ACC flow instabilities and respectively represented by the green and red dots are diverted with it, resulting in an increase in their concentration upstream of the ridge. So, the Pacific Antarctic ridge prevents their interaction with the marginal ice zone, favoring the formation of the sea ice protuberance downstream of the submarine relief itself, like we saw at the beginning of this presentation. Once the ACC flow reaches 150 degrees west, it crosses the Pacific Antarctic ridge in correspondence of the deep Udinse fracture. Here, a greater freedom of motion for eddies is present, which therefore results in less regular contours of the observed median sea ice extent and in the southern positioning of its northern edge, respect to the ice protuberance. So thank you very much for your attention. I'm really sorry that I couldn't attend the conference. However, for any question, feel free to contact me on my personal email address. Bye.
And next, I invite Dr. Alexandra Gossart. He'll be talking about conserving the radiative and freshwater fluxes through PWRF, MIT GCM interface in the Scripps cost model for the Ross region. SCAR IT team, please play the pre-recorded video presentation of Dr. Alexandra Gossart.
Access through polar warfare MIT GCM interface. The script goes. Hi, I'm Alexandra Gossart from Victoria University of Wellington. I will present conserving the radiative and freshwater fluxes through polar warfare MIT GCM interface in the script coast model for the Ross Sea region. This is work that has been conducted together with Aliona Malarenko, Mario Krapp, and Wilson. In this work, we use an atmosphere model and an ocean model. Usually, these models are run separately. In our case, we have coupled them, which means that they exchange information between one another. The ocean gives information on sea surface temperature, ocean current, and the presence of sea ice to the atmosphere, and the atmosphere sends back information on solar radiation, turbulent fluxes, wind, rain, and snow. This enables a better representation of sea ice, of polynyas, and interaction between the two, between the atmosphere and the ocean. In addition to this atmosphere and ocean, there is also the presence of snow and sea ice and snow overland that is taken into account in the atmosphere. The ocean has a routine that generates and moves around sea ice and an ice sheet model that can be turned on or off. And the ocean has a sea ice routine that generates and moves around sea ice and can also have an ice sheet module, which is turned off for these simulations here. In our model, the atmosphere is taken care of by the weather research and forecast model in polar mode, the polar WRF. The ocean comes from MIT GCM model that also has a sea ice routine and an ice sheet. Those two models talk to each other through the ESMF NUO-PC coupler. This model has been published as a script coast model in 2019 by Sun et al. And some adaptations for the sea ice over the Southern Ocean was made available to us by the same group. We present here a regional coupled ocean atmosphere model over the Ross Ice Shelf in Antarctica, delimited by the red box on the left-hand side. This model has a horizontal resolution of 10 kilometers, and both models have exactly the same grid. They exchange every time 10 minutes. The model is forced by RFI for the atmosphere and SUS for the ocean. We had to fiddle to adapt the land-ocean mass for both models and make some topographic adjustments so that the ocean circulates freely. We generated 2 times a 1-month simulation for January 2016 and August 2016, but the results presented here concern January only. One of the first challenges in ocean-atmosphere coupling is that in the sun case, the published case, air temperature, wind, and humidity were used both in the atmosphere, the blue part, and in the ocean, the red part, to generate latent and sensible heat flux, the shortwave and longwave net fluxes. This was a problem because those fluxes were not exactly calculated in the same way and not using exactly the same parameters, which led to slight differences in the fluxes. In the work presented here, the balance flux, we made snow and calculated the latent and sensible heat fluxes, long and shortwave net, into the atmosphere, and those were directly sent into the ocean. Those fluxes are calculated over the sea ice and over the ocean, and the model grid cells can be either sea ice, ocean, but can also be partly sea ice, partly ocean. The models usually deal with it by weighting the different variables over the ocean and over the sea ice by the sea ice cover. This is done in the atmosphere, and in the direct import, as we used to do, this was also taken care of by the ocean, leading to a double calculation for the presence of sea ice into the atmosphere, but then also into the ocean. We changed this by directly importing the sea ice value and the ocean value for those fluxes into the MIT GCM that does the sea ice weighting only into the ocean and not into the atmosphere anymore. All the snowpack calculations are made into the atmosphere part because it's more complex and has more layers. Then the snow and sea ice information is sent into the ocean. All the fluxes changes because of the presence of sea ice were also taken care of into the atmosphere, and those fluxes are then directly sent into the ocean. We also discovered that the sea ice thickness and the snow and sea ice thickness have a huge impact on the latent heat calculation in the coupled model. Initializing it with too low values led to very high and very negative latent heat fluxes. It's therefore very important to initiate the model with accurate snow and sea ice and sea ice thickness values. Finally, we took into account the presence of meltwater that is not refrozen directly into the snowpack for both the sea ice, but also land into the MIT GCM the ocean model. We did this by integrating the value of that meltwater runoff along the ice shelf and putting it into the ocean at the front of the ice shelf in form of a freshwater river. The illustration on the right is not from Antarctica, it's from Svalbard, but illustrates what we have represented in the model. Here are maps of the different fluxes a few time steps into the simulations. You can directly see that the sign and the magnitude of the fluxes are rather similar. And the first column represents the atmosphere flux, the second column represents the ocean flux into our balance case, and the third column represents the fluxes into the sun case, that is the published case before we made our changes. And we can directly see that the short wave is the flux that shows the largest discrepancy between the second and the third column. And this is probably due because of the snow cover and the albedo representation that is very different between the two models. This is a time series of the different fluxes over the whole month of January, and the fluxes are integrated over the whole of the domain. The dotted line represents our balanced simulation, and the solid lines represent the sun case, the red being again the ocean, and the blue the atmosphere. We can see that the magnitude of the peaks change, and there are divergences the longer we get into the simulation. The latent heat fluxes are larger over the ocean in the MIT GCM, the sun published case, and there is a 10 to the 13th Watt increase in that simulation compared to the other ones. The sensible heat fluxes discrepancies are associated with the precipitation, where there is a lot of heat from the ocean in the sun case and a heat gain for our coupled model. The long wave net is slightly underestimated in the sun case, and the precipitation is accounted for twice in the sun case. That was a bug in the code that is not now resolved in the balance case. The evaporation diverges over time because of the skin temperature, and the runoff is accounted for in the coupled model and was not present in the sun case. Regarding the short wave, there's a larger maxima for the sun case, which is due to the different response to flux calculations. We can then say that the coupled polar warp MIT-GCM models makes the conservation of heat and mass possible over long-term simulation, which is very important in the frame of future projections. But there's a little bit more work to be done. We want to harmonize and exchange the albedo calculation between the two models. We also want to implement a two-way exchange of snow and sea ice variable. At the moment, it's sent from the atmosphere to the ocean, but not back from the ocean to the atmosphere, which is an issue because sea ice moves over time, and that is not accounted for, leading to relict of snow and sea ice layers over ocean cell once the sea ice has moved from that cell. We also need to adapt the ocean component to the fluxes coming from the atmosphere because it was tuned to get the direct temperature, wind, and radiation terms and calculate its own fluxes, which is not the case anymore. Thank you very much. Do not hesitate to contact us. Our email addresses are here, and we will shortly submit this paper. Thank you.
Thanks, Alex, for this excellent talk on the efforts undertaken to couple the ocean model, MIT general circulation model, to the atmospheric polar weather and research forecasting model over the Rossi domain. I think she is available in person. If I would request audience, if you have any questions, she'll be happily take up these questions. So in chat box, there are no questions. So let me move to the next speaker. And let me invite Ms. Kshitija Suryavanshi for her talk on unusual sea ice conditions around the Antarctica from 2016 to 2021. Kshitija, please start your presentation.
Yes. Hello, good afternoon to all. I am Kshitija, a research fellow working at NCPOR, Goa. The title of my research today is Unusual Sea Ice Condition Around the Antarctic from 2016 to 2021. Today, global sea ice condition is a concern for every one of us across the world. The variability of the sea ice at poles acts as a key indicator to climate change. So coming directly to the variability in Southern Ocean, figure A represents the yearly sea ice extents from 1979 to 2021. The global warming has experienced a tremendous decline in Arctic, but Antarctic has observed an increasing trend till 2015 that marked the highest ice extents in 2014, that is 13.18 million square kilometer. But recently, the sea ice trend has declined more than 5 times from 1.95% per decade to 0.38% per decade from 1979 to 2021 to mark the lowest ice extents in 2017. The plot below shows the month-wise ranking of sea ice extents for each year from 1979 to 2022, where high rank represents high sea ice extents and lower rank means lesser sea ice extents. It is clearly shown that the lowest ranks are more dominantly observed from 2016 onwards, along with record low values as shown in the magenta colored points. However, the models magenta colored points is shown as a record low values, and however the model data has shown the consistent decline in sea ice post 1990, that is contradictory to the observation. The decline in sea ice cover has justified by by the anomalous rise in atmospheric temperature after 2015, as shown in the blue line plot in figure A, that is calculated by ERA5 data. Highlight. The decline is highlighted in the magenta colored box from 2016 to 2021. The sea ice deviates largely in Weddell, Ross, and Indian Oceans as compared to other sectors to mark the tremendous decline from 2016 to 2021. The spatial anomalies here are shown in the first left side of the plot. It is of the sea ice concentration from 2016 to 2021 that observe an overall decline with maximum in summer and spring seasons. The retreat in summer is highest in Weddell Sea, eastern parts of Ross Sea, and also in the coastal parts of Indian Ocean sector. The distribution of sea ice in winter and spring season follows nearly heterogeneous pattern of higher and low concentrations observed in Weddell, Indian, and Ross Sea. While a distinctive feature of three troughs and crest is detected in the winter season. Correspondingly, the sea surface temperature also shows an increasing and decreasing anomalies. The higher amount of vapor content over the Southern Ocean represents higher poleward transport of this warm air, increasing the air temperature and the surface temperature of Southern Ocean. The occurrence of the troughs over the Southern Ocean influences the northerly transport of moisture. The air temperature here shows anomalous warming in the Weddell Sea in summer, autumn, and spring seasons. The winter season, that is June, July, August, observed the asymmetric distribution of temperature with alternative lows and highs. This asymmetric distribution is due to the amplification of zonal wave 3. The zonal wave 3, it is the asymmetric distribution of the component of circulation. It is marked by three alternating lows and crests, that is the troughs and crest pattern of the atmospheric pressure centers located in Indian, Pacific, and Atlantic sectors. The figure on the left is the normalized geopotential height anomaly for the winter 2017, where the black small dots represent the GH anomaly greater than 2 standard deviation, while the plus mark represents the geopotential height anomaly greater than 4 standard deviation. The ZW3 index is calculated using the following formula as shown in the slide, and it is calculated for the 3 points, three points that are shown in the white dots. 79.5 degree east, 32.25 degree west, and 139.5 degree west. The variability of ZW3 amplitude is stronger during winter and spring seasons. The representation of ZW3 index shows increase in the positive phase, while the negative phase has reduced from 2016 to 2021 compared to 1979 to 2015. The ZW3 index shows dominantly positive phase in overall time period from 2016 to 2021. The positive phase of ZW3 index denotes the meridional flow and negative phase denotes the zonal flow. Of all, 2017 has observed an unprecedented sea ice decline. The decline in summer 2017 is attributed to amplification of ZW3 index and the negative SAM index that has deviated the ice extent to the lowest in March in favor of the record negative MSLP between Ross and Amundsen Sea. The amplitude of ZW3 is an indication of large-scale temperature gradient. These steeper temperature gradients influence the poleward transport of cyclones during winter 2017 that led to atmospheric warming, creating the extensive ice-free region and more declining sea ice concentration. This is the spatial representation of the amplification of zonal wave in the winter season. It is a seasonal anomaly from 2016 to 2021 for winter season. it clearly shows the impact of sea ice through the increased total water vapor, surface air temperature, and the increased SST that impacts the sea ice condition. And you can clearly see the wave 3 pattern of the 3 troughs and 3 highs in the sea ice pattern. For the future work, I am going to work on the teleconnections in the tropical ENSO and the ZW3. So the poleward propagation of Rossby waves enables to develop the teleconnection between ENSO and extratropical climate. These waves are developed during the winters of southern hemisphere in the higher geopotential heights during the El Nino phase. In El Nino conditions, the warm SST in tropical Pacific enhance the tropical convection and meridional equator to pole thermal gradient. The convection generates stationary Rossby wave trains and forms a signature of wave that is related to increased SST exceeding 27.5 degrees Celsius. This tropical convection then hits the mid-troposphere and accelerates the Hadley circulation that leads to equatorial shift of subtropical jet. The strength of this STJ reduces the storm activity in South Pacific. South Pacific that further impacts the strength of this Ferrel cell. Thus, through the variation of the meridional heat flux, the same tropical warming then shifts the zonal circulation eastward to descent into the tropical Atlantic. Consequently, the storm tracks shifts poleward in South Atlantic. The changes in the jet stream and the regional Hadley cell apparently result in the weakened Ferrel cell in the South Atlantic. The opposite conditions arise in the La Nina conditions as well. So this I'll be keeping as a motivation for the further work. Summarizing the presentation, the rate of the increase in sea ice concentration.
You can complete your presentation,
yeah. Has declined to 0.38% per decade. That is more than 5 times as compared to decadal expansion during 1979 to 2015. That is 1.95% per decade. The sudden drop in sea ice in 2021 reached the lowest in December 2021 and early 2022. That is similar to the situation in 2017. Recently, a new record low sea ice extents that dropped by 31% below the mean in February 2022 and 13% below the average in June 2022. The amplification of ZW3 observed number of effects on sea ice conditions in Southern Ocean, such as frequent cyclones, asymmetric distribution of sea ice, affecting the advancing and the retreating time of sea ice. The warm air advection due to poleward movement of cyclones and increased vapor content has significantly increased air temperatures and net gain of heat flux by the ocean. The top 4 record lowest sea ice extent years were observed since 2016, corresponding to warmest years dating back to 1970. Whether this hints to the warmer climate shift with consistent sea ice decline under the increased anthropogenic forcing as predicted by various coupled model intercomparison, that is CMIP6 models. Thank you so much.
Thanks, Idija, for talking on the unusual Antarctic sea ice condition around Antarctica. If there are no questions, let me go to the concluding remarks. I think already session time is over. So we have completed the first part of the session. On behalf of all the convenors, I am thankful to the keynote speaker, all speakers, participants, SCAR team, most importantly, the technical staffs for successful conducting this part of the session. And this session will be continued tomorrow at 11 UTC, hall number 1. I would request Dr. Anil, Kumar, Dr. Sabu, do you like to add anything?
Yeah. See, actually, this session is very informative and a lot of, because this is a very changing scenario. Now the warming, global warming condition is coming, and we understand that the drastic change in sea ice conditions from 2016 onwards and record lows, also we are getting this. The study about the sea ice conditions is very, very important to address about the what will happen in future. The keynote speaker also in 2100, how it can be if no sea ice conditions or a little bit existing sea ice conditions, such kind of things has been discussed with the model. So this is this area of study is very, very important to understand about the Antarctic sea ice conditions and how it affects with the climatic, tropical climatic conditions. This is very important session. I am very happy to attend this session.
Yeah, from my side, it was an interesting session. Talked about different models and several ocean processes affect the sea ice variability. So it was an interesting section. So I take this opportunity to thank all the speakers. Thank you.
Dr. Sabu, you can take one of these photographs.
Yes. Yes, done.
Thank you. So, shall we close the session?
Yes.
Yes.
Thank you so much. Thanks a lot. Thanks, Tom.